If 20 adult workers are randomly selected, we want to know the probability that at most 12 of them have a high school diploma but don't pursue any further education. We know 41% of adult workers have the high school diploma and do not pursue further education. In order to answer this question, we want to phrase the given information as a binomial probability distribution function. We'll let our random variable represent the number out of 20 adult workers who have a diploma but do not further their education. That means our variable can take on values ranging from 0 to 20. Our variable follows a binomial distribution with 20 trials and a 41% success chance. So that means n, the number of trials, is 20. The probability of success is 41%. Those two numbers together are all we need to determine the binomial probabilities. And that's why those two numbers are the only ones that show up in this binomial probability notation. So the capital X, squiggle, capital B, and then in parentheses we have n, comma, p. That's how we denote that we're looking at a binomial distribution function. Once we know p, we can figure out q by finding the complement there. So we know the number of trials, the probability of success, and the probability of failure, and we've defined what it means to be a success when we defined what the variable x is. Now the question that we want to answer is, what's the probability that at most 12 of these 20 adult workers have a high school diploma but do not pursue further education? We're looking for the probability that our variable is less than or equal to 12. And we could use a graph to help us answer this question, where we have bars representing the probability for each variable value. And since we're looking at all of the variable values less than or equal to 12, we know that we're looking at multiple bars added together. Now in this case, because we're saying all the values less than 12, we could use what we call a cumulative binomial PDF, or rather a binomial CDF, cumulative distribution function. And just like cumulative relative frequency, it's adding up all of the probabilities at or below the number you're picking. So the binomial CDF for 12 would give you all the probabilities at 12 and below 12. Either way, we're getting the sum of about 97%. So there's a 97% chance that if we pick 12 adult workers at random, 12 or less will have a high school diploma but do not pursue any further education. In addition to that idea, we can talk about an expected average, or the mean, for a binomial distribution. And you're going to love this. It's very easy to calculate. Earlier I said the two most important numbers about a binomial PDF is the number of trials and the probability of success. And in fact, those are the only two things you know, or need to know, to calculate the mean. The mean is just multiplying n times p. So in this case, mu, our mean, is 20 times 41%. So we expect on average, out of the 20 adult workers, about 8 of them will have a high school diploma but do not further their education. We can calculate the variance, which is a measure of the spread within our data, multiplying n times p times q. And then if we wanted to, we could use that variance to calculate our standard deviation. All we need to do is square root the variance to find the standard deviation. So if our variance is 4.838, then our standard deviation is the square root of 4.838. And we use sigma for our standard deviation. So sigma is about 2.20. So for a binomial probability distribution function, calculating the mean comes down to multiplying n times p. Calculating the standard deviation is the square root of n times p times q.